Hello and welcome. In this video, we're going to take a look at a technique of differentiation using logarithms. No surprise, it's actually just called logarithmic differentiation. And what we're really doing is we're using the properties of logarithms to be able to avoid some of the common struggles with differentiation, such as product and quotient and sometimes chain rules. There's often some functions that involve a great deal of those different rules, and we can try to avoid them by looking at properties of logarithms. A little unsurprising that when you take the logarithm of a product or quotient, that you can split that up into separate logarithms. So let's see when this might be useful. We're going to be looking at functions of the form y equals f of x, where when you want to find the derivative dy by dx, you find that differentiating that function is going to be a lot of products and quotients and probably some chain rules too. So what do we do? What's the technique here? Well, we're going to start off by taking the logarithm of both sides, and we'll use the natural logarithm. Given that the natural logarithm, ln, is a one-to-one function, by taking the logarithm of both sides, we haven't changed the value of the equation. Now, we'll apply implicit differentiation to both sides. And the first step in implicit differentiation is to apply the differentiation operator to both sides of the equation, here d by dx. Now, we'll have to use some chain rules here. When we take the derivative of the natural logarithm of y, well, we'll get 1 over y, but we have to multiply by the derivative of y. And we'll have to use the chain rule on the right-hand side as well. The derivative of the logarithm of the function f is going to be 1 over f times f prime. But this is really the important part here. On the right-hand side, when we have the logarithm of the function f of x, if there are several products or quotients or chain rules, then we can probably use properties of logarithms to simplify. And here are the three important properties of logarithms that you can use to simplify that right-hand side. So rather than just using the chain rule and product rules, we'll assume that at this step here, hopefully that right-hand side can be simplified, and then we can just differentiate each of the individual logarithms. So I'll just continue to write that as being generally just the derivative of that right-hand side, where this will become a lot easier than just differentiating the original function. Now, I'll leave that right-hand side alone. We're hoping that that is going to be an easier derivative now, but the last step here is to get dy by dx by itself. The last step of implicit differentiation is always to solve for this derivative. And now we've got the derivative dy by dx by itself, but since we are given an explicit function y equals f of x, we should really state our derivative in the same form and have it just be in terms of x here. So in order to do that, we're just going to make a small little substitution where y is equal to f of x. So last but not least, we end up with the derivative dy by dx is equal to the function times the derivative of the logarithm of that function. And remembering that taking the logarithm of that function will allow us to use several properties of logarithms to make that derivative a little easier. Well, let's try an example of this. Right, well, here we have a function y equals root x times 3x squared plus 5 all cubed, all divided by 2e to the x. And so you can see we've got a power rule with root x, another power rule with 3x squared plus 5, and an exponential rule. But we've also got a fairly large chain rule, as well as product and quotient. So this would be a terrible derivative to do without logarithmic differentiation. Let's see how it turns out with this new technique. The first step in logarithmic differentiation is taking the logarithm of both sides. And now, before we start taking derivatives of both sides, let's do that simplifying process. On the right-hand side, we can split this up into the logarithm of the numerator minus the logarithm of the denominator. And that's not even close to the amount of simplifying we can do, because we still have a product, root x times the polynomial here cubed, and we have what could be another product of 2 times e to the x here, and that can be split up as well. And be careful when we split up this product of 2 and e to the x that the negative sign needs to be distributed. Well, we have lots of logarithms now, but that's still a little less intimidating than having to have products and quotients. There's still more that we can do here, because you see that anything with a power like this root x or 3x squared plus 5 all cubed, we can have those powers end up in front of the logarithms as coefficients in our next step. And last but not least, using the cancellation property of the natural logarithm and natural exponential functions, the logarithm of e to the x is just equal to x. And we're finally at a stage now where if we look at what we need to do for the derivative, we only really need the chain rule. We've gotten rid of all of these additional products and quotients, and we've actually got rid of most of the chain rules as well. There's really only a chain rule here, where we look at the logarithm of 3x squared plus 5. We can't split that up. And really a chain rule over here with the logarithm of y when we're doing our implicit differentiation. So now we're ready to differentiate both sides. Remembering that when we differentiate the natural logarithm of y, we end up with 1 over y times dy by dx. And on the right-hand side, we have several constant multiples as well as a chain rule. Now, remembering with the chain rule of a natural logarithm, the derivative of the logarithm of this stuff here is going to be 1 over that stuff. And then the product rule, we have to multiply by the derivative of the inside function. The derivative of 3x squared plus 5 is 6x. And when we multiply that, we can multiply numerators. It's easiest just to write that as 6x over 3x squared plus 5. And then, of course, the 3 and the 6 could multiply in our next step of simplifying. Now be careful, the natural logarithm of a number is simply a constant. And so when we take the derivative of a constant, this will end up being 0. And the derivative of minus x is going to be minus 1. All right, we've done the derivative. We just need to isolate dy by dx and get rid of this y. To get rid of the y, remember that the original function was this terrible looking one up here in black. We just need to basically copy that and replace the y with that expression. And there we go. We've got our derivative. And you can see that a lot of the mess was avoided, although the final answer is still quite a mess here. If you were to try the same process without using logarithmic differentiation, you would get an equivalent answer. But presumably it would be all one fraction, and it would be just a terrible mess. You'd have to do a lot more simplifying. And we can just leave our final answer like this. Now, obviously this is one of the best uses of logarithmic differentiation, but it's not the only. In fact, there are certain kinds of functions that we can really only find the derivative of using logarithmic differentiation. And let me show you an example. Here I've got a pretty bizarre looking function. I've got a polynomial x squared plus 1, but it's to a power of sine x. And when we're trying to differentiate this, you might be thinking of a couple different types of rules that we've already looked at. If this was x squared plus 1 to a power of n, where n is just some real number, then we'd use the power rule. We'd simply bring n down to the front of our new power of x to the n minus 1. But this is not a constant. In fact, the power is actually a function of x. Well, that might make you remember another kind of scenario where we have e to the x or b to the x, with e or b being some base, which is another constant. But that doesn't apply here either. We've got a polynomial written to a power of a function of x. And so we can't apply a power rule or exponential rule. However, what we can really do here is if we were to write this maybe as y equals x squared plus 1 all to the power sine x, then we can use rules of logarithmic differentiation and evaluate the derivative that way. I find it's easiest to write y instead of f of x here, but you could just write f of x and take the logarithm of f of x. It's going to end up the same way. But if you write y, it makes the notation maybe a little easier with fewer brackets, so that in our next step, we're going to take the logarithm of both sides of this equation. In doing that, using the properties of logarithms, we can then take our sine x, which is our power, and simplify this logarithm by multiplying sine x times the natural logarithm of the base. And that will allow you to use the product rule when we weren't able to use power or exponential rules. Now we can differentiate both sides. Once again, we'll have 1 over y. If you are using function notation, you'll have 1 over f of x, and then multiply by the derivative. And we'll use the product rule on the right-hand side. Don't forget the chain rule in one of the two terms of the product rule. And then we're ready to multiply both sides of the equation by y, and we can put this back into a function of x. And in this last step, I've just plugged the function f of x back in for y and written the derivative back in the form f prime of x. Now really this is about our only way of handling derivatives of a function in the form of some function f of x to another power g of x, where x appears in both the base and the power. We'll have to use logarithmic differentiation to handle that kind of circumstance because the power rule and exponential rule can't handle having both the base and the exponent as having the variable. I hope that gives you a pretty good alternate way of hiding some of your product and quotient rules behind logarithms. As it turns out, finding the derivative of the natural logarithm is actually fairly straightforward. Don't forget, you're probably still going to have chain rules there. And then don't forget that whenever we have some sort of function of x written to a power of a function of x, that you're going to need logarithmic differentiation. It really isn't an option in that case. Well, anyway, we'll see where this can be applied in future videos. Thanks for watching. I'll see you in the next video.